Hey guys, what's up? Eddie Aho here with KISSanalog.com. Today I want to talk about power dissipation and resistors. Welcome to another episode of Kiss U. This is on power dissipation. We're going to measure it with a thermal camera like this, or an IR meter like this, or maybe a thermocouple like this. This is kind of a cool one. Or just a little wire like this, another thermocouple type. So we can measure it with one of these thermocouples, maybe something like this. Looks like one of these kind of things, right? This dude, or this guy. Alright, we're going to measure a resistor under temperature, and well, I'm getting attacked by a Ktype thermocouple. That's what that is. Alright, hey, okay, so when it comes to resistors, they come in all kinds of sizes: through-hole, surface mount, big old power resistors like this, 200 watt rated guys. So they come in all kinds of different forms, and got some more of these resistors. Big guys, big old coil looking things like this, big dude like that. And here's some smaller big guys. So flat. So yeah, resistors come in all kinds of sizes and shapes. Little small surface mount guys, and they all have power ratings, and we have to know how to use those power ratings. Okay, so this is just a quick video and a demonstration to show what that is. Now basically I'll just say one thing right here, is that we talk about derating. So derating is a new term. So when you use a part, say it's rated for 1 watt, you derate it so that you say that really a 1 watt part's really a half watt part, or a 500 volt part is really a 250 volt part. So that's derated by 50%. Okay, so often with capacitors we derate them, say 70%. So we only use about 70% of the rated value. With resistors, it's a common story that we hear 50%. Okay, so what I want to say and what I want to demonstrate here is that 50% is a minimum. If you have a half watt dissipation, you need a certain resistance value, and with the voltage or current that you're going to have, you're going to end up with a half watt. Well, you could say, okay, I'll get a 1 watt resistor, I'm good. Well, that might be true, but I would suggest going to 25%, derating down to 25% or 30% to play it safe. Resistors, well, unless you're getting these big resistors, most resistors are inexpensive. Very little cost to them. Even a 1 watt resistor doesn't cost very much. Most resistors you're going to deal with are going to be small. Even if you're in power electronics, a lot of times you might have some sense resistors that might be 1, 2, 3 watts, or you might be using 3 1 watt resistors to give yourself 3 watts. But you might only be dissipating 1 watt in that, okay? So that 50% thing, take it with a grain of salt. I'm going to show you some data here to help you learn on your own how to do that. I got a really good data sheet here, and I'm going to show a demonstration. I think we're going to use one of these big old resistors here. Now another thing about resistors, this isn't a full resistor type kind of video. It's just power dissipation type. But just to mention that some of these resistors I showed, like that's obviously a coil wound resistor. It's actually a coil wrapped in a coil. But this is a wire wound resistor. It's got a wire wrapped around. They wrap it around one way, and then they wrap around the opposite way. And when they wrap it around one, what does it look like? It looks like an inductor, right? So it is an inductor. I mean, it's a resistor, but it has inductance. So to make a so-called non-inductive resistor, they wrap the wire back the other way, and the field, the magnetic field that is produced by the coil going in one direction is canceled by the coil going back the other direction. So I can tell, it's hard to tell. I could bring the camera up and show you this, but anyway, I don't want to really go into a lot of different types of resistors, just kind of explaining that there are wire wound resistors that are a lot like an inductor. And we talked about parasitics in other videos. Those are parasitics. When you have a resistor and it has inductance, that's kind of a parasitic effect, something you don't want but you end up getting. So some of these resistors, the wire wound type, they've learned how to make them non-inductive, or pretty close to non-inductive. A lot of resistors, a lot of surface mount resistors are metal film resistors, and there's thick and thin film metal resistors. Again, we'll cover all those technologies in better detail later. I just want to bring it up just because the different technologies do have a little bit different derating. Okay, one thing about a resistor, or especially a resistor, when you turn on power and the resistor is going to be hit with some current, okay? When the current goes to that resistor, it creates heat and power dissipation. So when it does that, let's say you have a surge or spike and that resistor is meant to be part of a snubber, part of a filter network that's going to see spikes. Well, or it's a current sense resistor in a switch mode power supply that's going to see pulses. You want resistors that are pulse rated. So what that means is some resistors, when you hit them with a current and develop some heat quickly, there's a thermal lag. It takes time for that heat in that hot spot to spread out through the resistor, okay? And depending on what kind of resistor you can get resistors that perform better in that kind of operation. And so, you know, resistors aren't just resistors. They come in all kinds of varieties, just like capacitors. So there is a common theme: dissipation. There are some resistors that are meant to run super hot, high temperatures, and when they cool down, they don't change their resistance. If they were, say, 1 ohm when they started and they got really hot, 200 C, some real hot temperatures, when they cool down, most resistors, even if they ran at some rated temperature, they may change value when they cool down. But there's other resistors that are designed to actually operate that way. But most resistors, if you overheat them, they'll change value. And some resistors, a lot of resistors will also change value as when they're hot, because with heat it creates more resistance, and so the electrons have a harder time flowing through something that's hot with the atoms all going crazy, okay? So you want to keep your resistors cool. And there's also another phenomenon. There's when you have two different metals touching, say a connector or something, you can actually get a voltage developed at that junction just by heat. Kind of crazy. And that's actually what is happening in some of these temperature type devices. So wire here, there's two different kinds of wire, different kind of metals, and they actually create a little voltage that's detected in the meter. So in your circuitry, you don't want that kind of thing happening. And honestly, I never really have to think about that. One thing I always do with resistors, I always make sure they're derated plenty. I usually try to derate down to 25%, 30% maybe at max, okay? I never go to 50%. Okay, so let's bring you over to a notebook. I'm going to show you some power equations, and we're going to do a demonstration here to show you not only how and why and when you might want to use these different kind of measurement tools, but you'll see why we want to use a different kind of tool. You know, like say that thermal lag I was talking about. if you don't have time to let your device, your type of thermal instrument, to change temperatures, you want to be able to capture fast moving things, you might want to have a camera, okay, or an IR device, something that it works almost instantly, okay. If it's something that's going to heat up slowly, then these thermocouples will work great, okay. All right, hey, let's bring the camera over here and let's do it. Okay guys, so what I wanted to show you to begin with is this data sheet, application guide actually, R35 from RCD. I suggest you pull up this. I think I'll leave a link in the video so you can link to this. This is a very nice application guide. So what I want to show you is a resistor. This is a depiction of a through-hole resistor. The PCB board with the leads of the resistor. And what this is showing is there's 3 ways to get rid of heat, not just in resistors but in most parts, okay? So one way is just radiation, just heat radiating off it, like you see the heat radiating off a hot highway, right? Just those heat waves, that's these little lines here, just radiation, okay? Another way is conduction through the leads into the board. Alright? And then if you have airflow, then you can have convection. Okay? So that's radiation, conduction, convection. Alright? Now, if you have a hot resistor on a board like this, it will radiate heat because it's so hot. And it'll also conduct, and if it's really hot, it might put about 50% of heat out in both directions, in radiation and in conduction. Most often what you want to do, if you are going to run a resistor hot, you think it's going to get hot, is mount it like this so that it's not sitting on the board. They have little tools that they'll bend the leads so that they sit down on a little bend right here, and they don't go all the way down. Alright? But most often with surface mount parts and most of your resistors, they'll mount right down to the board, and you want the leads nice and short and big heavy copper pads to pull the heat out of the part, okay? Now another thing I want to show you about this is they have a lot of information there, but they have all these resistor types that they sell. What I want to have you focus on are these through-hole. These are surface mount parts, sorry. 0805, 0603, these are the sizes, the length and the width, okay? 2512 is a 1 watt. So a 1 watt resistor is going to heat up 75 degrees C per watt. So if you put 1 watt in that, it's going to heat up 75 degrees. So if you're sitting at about 20 degrees Celsius room temp, or just above 20, you're going to be almost 100 degrees. You don't want something at about 60 C, it's too hot to touch. So you don't want to heat it up that much. That means that if you did a half watt in that, it's going to be about 35, 30 something degrees plus the 20 something degrees. It's going to be almost too hot to touch at half a watt. So that's why I say 1/3 of a watt is about right. And you can see from these other sizes, you kind of do the same kind of math on them, okay? Here's a 1 watt over here, same thing, about 100 degrees C per watt. Now this one is a different kind of 1 watt. Here's another 1 watt, 110 degrees C per watt. So the surface mount, because the leads are so short and that it's mounted right to the board, it actually runs the coolest of the other, the through-hole parts. And it has a lot of surface area because it's flat, right? There's surface mount. Okay, I just wanted to show you this. But what I want to do in this demonstration is I have this 200 watt resistor. You can see how big it is, okay? It's 8 ohms. See, it's a little over an inch high. And it's sitting on this mat here, so it's kind of a silicon mat, so it can take quite a bit of heat. And you might say, well, we're going to put 100 watts in that and see how hot it gets. But I don't even want to do that. I'm going to put about 70 watts. Okay? Alright guys, so what I want to do is I want to point out Ohm's Law will, V, R, I, right? So you get these three equations. If you want to solve for V, you just cover up V, and then it's R times I. V equals R times I. You want to solve for R, you cover that up, and it's V over I. V over I. And you want to solve for I, V over R. I equals V over R. So that's just Ohm's Law will. Now there's a power will. Okay? The power, P and V and I. So you cover up P, V times I, cover up V, P over I, or cover up I, and it's P over V. Okay? Now there's something kind of cool that comes out of this. If you look at the equations here, take this equation here, P equals V times I, but you can also get some other forms. You can get rid of the V, so you can get the equation up here, V, I put an asterisk there, V equals R times I, so the asterisk here, V equals R times I, so you put the R times I in here, then you have two I's times each other, so it's I squared, so it's R times I squared. But there's also this one, you can get rid of the I, and you come up here and say, well, I is equal to V over R, the double asterisk. Double asterisk here, I is equal to V over R. So you put I in here, so it's going to be V squared over R squared, but you have R times, so one of the R's cancels, so it's V squared over R. So you have your three power equations, this one, and this one. So now we know we have a 200 watt resistor. What I want to do is I want to put 3 amps into 8 ohms. So let's do that math. 3 squared, enter, 8 times 72 watts. Okay, let's do 72 watts. Okay guys, so this one is going to have the current. I got the power from the power supply coming in the red and blue. So the positive comes in the red, goes down here into the resistor terminal, up here through the resistor, okay, and then the blue, so then it's going to go through the resistor, out this one, through the yellow one, into the current, and out the common back to the power supply. So this one we're going to be able to see current, okay, got to get the glare off that. Alright, so we'll see the current here. Right now I got almost half an amp and about 4 volts. Okay, so let me bring the power supply up so we can get 3 amps here. And you'll see the voltage, because the voltage right here, this probe is tied right here. So we're looking at the voltage going into the resistor. Okay, we're at 1 amp. You can hear the power supply buzzing probably. It's a big old HP power supply. Got it out of my storage. Okay, there's 3 amps. Pretty darn close, right? We have about 24.4 volts. So you could go V squared over R, or you could go I squared over R. Same thing. Now right now that resistor is pretty cold. So I have several different thermocouples. I have this one going into this meter. So when I turn it on, it takes a minute. See, 19.6 degrees on the mat. That's Celsius. This thing, resistor looks like it's gotten up maybe a couple degrees. Okay, and then I'm putting this meter here. Turn that guy on if I can. This one has this kind of interesting probe. It's a little filament right there. It's 2 wires, very similar to this less expensive guy. These are both Ktype thermocouples, so they have dissimilar metals that change with temperature. They create a little voltage. This one has a little bead right here at the tip. So let's see, I have to get this meter set up for current, or for temperature. Put that Celsius. So yeah, 19, 20, pretty close. So I can touch this down here. Wow, that guy's up to 32 degrees already. But see how fast that changed? This thermocouple is actually pretty fast for a Type K. These Type Ks are usually not super fast. That guy goes up pretty fast. Now this one I have on the astrometer. This is just this kind of thermocouple here. Just this wire. Looks like a real simple wire. Let's see, I'll put that underneath here so we kind of see the display. Kind of covered a little bit. Whoops. Hitting buttons. Okay, so this thermocouple, I have this little putty. I'm going to put it right here in the middle, and I'm going to put this putty on it. This resistor is getting hot. We used to call this monkey poo. See if it'll hold this guy down. This wire is pretty stiff. So when you sometimes you glue these things down, this little putty helps. This resistor is big enough that we're not going to change the temperature too much by adding that. But you can. Let's see, this guy. Okay, so this one says 45 degrees. Now that kind of thermocouple is very slow. So this resistor's heating up slowly, so that works. But you can see how fast this one works. This guy here, I'll take it off later and show you how slow it changes, but it changes slowly. So that's why you want to hold it down with something like that putty. So we're up to about 48C. Starting to get kind of hot, right? Okay, now this guy here, let's turn that on again. Wake it up. Okay, you can see how fast that changes. So I put over here 19.8. And it really works good when I point it at the putty. One thing about metal, especially if it's shiny, sometimes these IRs can have a problem reading. Is that 49 degrees? So you can kind of see all these different methods to do it. The IR ones work really well. That's why people have really started using these. And you get these kind of things inexpensively now. Back when I got this Fluke, it wasn't really cheap. I can't remember what this thing costs right now, but it's like 150, 200 bucks or something. But now you can get them pretty inexpensively. They use them for cooking and everything now. But yeah, so you can see this guy here. Here, I'll show you something here. I'm having a little trouble. Now this meter here says 59. So that's getting, that's where I don't really want to keep my finger on there very long. Now let me show you something with this thermocouple. That's the way it comes. It has these little K-type thermocouples. And then this plugs into here, and then it plugs into here. And so when I move it around a lot, it comes loose over there. See how fast that changed? 61. Changes very fast. I mean, that's a really fast K-type thermocouple. It's crazy fast. You can maybe you can see this meter, this IR meter. They change really quick too. So this one says about 58 almost. Let's see how they measure comparison. So I'd probably trust this K-type thermocouple. This was actually a fairly expensive K-type. I think I bought that on sale at Fluke one time. Okay, now the ultimate is the camera. Okay, let me show you that. Got to turn it on. Hopefully my battery's not dead. Now this guy says 69. That's only about 61. This says 70. Yeah, those two kind of agree with each other, these two K-types. This guy right here, If I put some black electrician's tape on this, it would work better. I think that reflection's not working so well. Okay, now I also have this IR meter. So I turn it on this way. Now it has a sensor right here and then an LED that helps me guide or aim. So see, I point it. I don't know if you can see that red. I pointed the meter right there so you can see it bouncing off the meter right here. So I drew an arrow right here to show where the actual sensor was, because depending on how close you are, you can have some parallax error, right? Where the beam, you know, they're kind of focused like this, and I think they're focused to hit about a foot away. But when I'm this close, I can't miss, right? When I let go, I think it'll hold the temperature, 79, 77. So this guy works great. Kind of aiming at that putty. Here, I'll aim off to the side. Yeah, a little bit hotter actually, 80. So, yeah, this guy, another guy I bought on sale. It's a Fluke 65. I think they're getting rid of these guys. I think that's how I got all these guys on sales. It seems like they go through. Okay, now here, let's hit that guy. Now up here, you can see the hot temperature. There's a couple guys that jump around. One's finding the cold spot, one's finding the hot spot, but up here it reports the hot spot. So that's 84, that one's saying. Now it's interesting, when you look at the resistor, most of the heat's towards the center of the resistor. You see that? See how down here on the ends there's not a lot of heat? Kind of interesting how the heat doesn't spread out as well as you'd hope. Now the mat is pulling some heat out of this resistor, but hey, 85C guys. This guy says 88C. So this one's super fast, and it gives you an idea of, you can actually see the hot spots and how the temperature's going out. You can kind of see where the putty is here, where it's kind of cool around the putty. Let me take this probe one more time. It's over here. Now look at that, 86 degrees. 89 right there. So yeah, that camera helps. Look, 90 degrees C. So that camera kind of helps you find the hot spots, right? If I come over here by the edge, temperatures drop off. So you know how I say it's like a sponge? Eventually that whole thing will become pretty much the same temperature. It's still heating up, you can tell. Okay, 91, 94 degrees. So you can see that's only 72 watts in a 200 watt resistor, and it is sitting flush on this mat, which the mat is fairly cool, not too far away, like 31 degrees right next to the mat. So it is pulling, look, 35 degrees right there. So it is pulling some heat into the mat. So it's helping heat sink a little bit. If I go a little bit further away, you see how the temperature falls off? 24 there. And come closer, it's 29. 33. So I'm sure right underneath it, it's pretty hot. So there's different ways to measure temperature, guys, and you can kind of see how hot 72 watts will heat up this resistor in the short time we've been doing this. Okay, I'm going to go ahead and shut it down. I think we're kind of proving our point. Last time I did this, it took this resistor quite a while to cool down. Alright guys, so 200 watt resistor. This is the 4 ohm version. It is made to go on a heat sink with these two bolts, okay? And when you put it on the heat sink, it'll help suck that heat out of this thing. And it doesn't really have the fins on it. It's made for, you know, conducting heat into a heat sink. So yeah, if you put it down on a metal plate. So yeah, I had it sitting here on this silicone mat that doesn't really, it absorbs some heat of course, but not like a heat sink would. So it allows this thing to get pretty hot, and also that thing can handle some pretty high temperatures, so I don't have to worry about it melting. But anyway, so yeah, you might be a little surprised. A 200 watt resistor can only handle not even close to that, but unless you heat sink something, that heat is going to, I think of heat, it's kind of like water in a sponge. You can put so much heat into the sponge before it can't take any more heat, like water into a sponge, right? That sponge will only take so much water until it's saturated. Okay, same with a physical device. You know, it can only absorb so much heat in a certain volume and shape and, you know, material before it's just saturated with heat, and that's it. Okay, so you need a heat sink. Alright, hope that makes sense. And if you like this, give me a thumbs up, guys. Appreciate it.